Hey, welcome back. We are still working on this damped pendulum problem, and last time I was getting to the point where equations of motion were in there. We were making some progress. I started to copy them down here. I'll put more into that as we deal with the LaTeX, kind of finishing up this Pluto notebook. But one of the main things that I missed was a factor of 1/2 in this mass matrix. So let's zoom in a little bit. And this ended up being pretty important because the determinant ended up being negative. It was as if I had negative mass when I was trying to solve for the accelerations in this thing. So really this should have been here and here. Those are really a divide by 2. So really I need like over 2 in both of these spots. And if you go through the math, you'll see that that's a spot where I had mixed up. So even here, like this is really an L over 2 times 2, which ends up being just that. So this 1/2 carries through. But small point, but it is important because otherwise this thing it's just not solvable and it's not really physically realizable. But with that, now I can actually plug in some constants. So I have kind of Newton per meter. This one's like a given kilogram per second. Here we've got Earth gravity, mass of our rod, and then meter length of pendulum bar. Still coming up with the same kind of mass matrix, and really I could solve for this. I could invert the matrix and multiply it over. It doesn't make sense to invert a matrix as a general solution. It's fine if you have 2 or 3 degree of freedom systems. Like in this case, it's 2 degrees of freedom. I could invert it, multiply, and solve for these 2 unknowns and have an exact equation. In general, inverting a matrix is just a big no-no whenever you have bigger degree of freedom systems. So I'm building up kind of general rule of thumb of what I would normally do. So build up the vector, build up a left-hand side matrix, and then solve for those. This little backslash operator, whether you use Julia or MATLAB. In Python, it's a solve command. It's really powerful. It has a lot of speed up performance to get you an answer without actually inverting the matrix. That's a whole nother class of like why do that versus actually inverting it. But it's good to know, like if you're kind of working on stuff. So I have my function. Now it is, because I have this ML over 2, it's actually solvable. I don't have like a negative mass matrix, like something ill-behaved. I can plug in the actual function here. I don't have to look at small angle processes. So I'm using this exact equation to see what would happen for like large angles versus linearizing it. Linearizing is great if I want to figure out like what is this damping, like how do I change this damping coefficient for small angles, and it's a great way to start. But I want to look at like what's happening for anything. Then through some of my troubleshooting, I did this like testing, try to test the derivative. So this is kind of a cool way. This is kind of new to me too, so I'll walk you through like what's going on. This function is creating like mutating arrays. So that's why one of the inputs is the derivative and one of the inputs is the current state. So in here, I'm grabbing the values of the current state and using that to change what the derivative is. So it's changing these values of dy. So in order to test the function, I need test derivatives, which I can just set as zeros because I'm going to overwrite them anyway, and then some kind of testing state. Then give it my testing parameters, which are all the things that I defined up here, and then plug that in and see that yes, if I'm at time 0 and I plug in 0.1 meters, 0.1 radians, a 0, and a 0.5 radian per second, then I get back 0 meters per second, 0.5 radians per second, and then negative. So if I'm stretching, if I have a positive x, it makes sense that my spring is going to stretch it backwards. And then over here I have a positive. Does that one make sense? Maybe. I don't know. I guess between the two of them. I was expecting a negative for both of them, since this one is a negative MGL, but we got some other things going on. Okay, so cool. Let's get into the results now that this thing's actually working. And we'll start off with just B of 1. And what I can see here is if I start off at 60 degrees, then I'll damp this motion, and over 10 seconds I'm starting to get to the point where it's around 0. This is a pretty soft support spring, so only 2 newtons per meter. Not a lot, but that's okay. The interesting thing is, like, what if I make it bigger? So 1 kilogram per second, that's a good amount of damping. It seems like it damps it pretty fast. The weird thing here is that it doesn't actually, adding more damping in this case creates less damping, which seems weird if you're not thinking about it. Well, it seems weird no matter what, no matter how you think about it. But let's create less. We'll do 0.1 kilograms, and we kind of see like, oh, well, that's weird. It is decreasing, but not as much as the 1 kilogram per second. So what's going on here? There's something strange. And we could go half. Let's do around this 1 kilogram per second, it seems to be damping it pretty well. And then 1.5. If we start increasing it, then it's still damping, but not as much. Kind of strange. So let's look at physically what's happening. We'll animate the motion, and here what I'm doing is plotting these things. I'm creating a for loop where I have a few different damping parameters and overwriting this one, and then create that ODE problem, and then solve it over here. Let's make this bigger. And you know what I didn't do? I didn't check our YouTube stream to see if I'm actually streaming, so I'm just gonna do that real quick and see what's going on. It looks like I'm live, and I'll make sure that my sound is working. I was just too excited. I think that was the problem. All right, so we're good. All right, thanks for letting me check that. All right, so I've got that plot. Now, I use Copilot again to do some animation help of getting me some help, because I wanted to look at the spring. I wanted to add a little damper over here. I don't want it to plot this motion. It adds, AI has been great for some things. It adds a lot of like sloppy code, so it's like a lot of this stuff, it's not exactly how I would do it, but it's not the end of the world, right? And the nice part is I can just hide it. Just remove it all, right? Just it creates a frame thing, it creates a plotting thing, and then I can say, okay, show me this solution that I just came up with. Actually, I do want to see, not this one. I want to delete this one. What I want to do is, yeah, I don't care about that one, but I do want my solution, this one. Let's grab this and put it outside. So this one's defining my frame data. Let's put this up here. So now I can kind of play around with like what's my current, so main thing, we'll say like 1 kilogram per second in here. And what I can see now in the animation is that with 1 kilogram per second and this kind of loose spring, it allows the motion. I want it to move, because the faster it moves, the more damping I get. Versus if I make it 10, kind of how we saw before, and rerun this animation, it'll just take a second to catch up. Because there's so much damping, it's not actually, there's so little X motion, but there's almost no damping. It's as if this is a solid structure. And the extreme could be, if I come back up here, let's look at an extreme of like 100 times, where yeah, there's a spring and a damper kind of supporting this, but it's basically a pendulum. It started at 60 and maybe it's at like 59.5 degrees after 1, but it very slowly. So the bigger that damping, the less effective it actually is in this case. Just something kind of cool. So we can get nice damped motion without actually creating like a damper on the hinge connection, or we can increase that damping and make it basically a harmonic oscillator again, where it's maybe there is some damping, but we're able to kind of lock it out almost. So that kind of wraps up what I was working on here with this damped pendulum motion, and then we even have like some code and general process for like how do you create each of these frames and then plot each of those frames, and then it lets us visualize, and again, how much the spring is really stretching, which I think is kind of the cool part here. Yeah, so if there's less damping, then it lets the spring stretch and kind of bring it back and kind of damps out the motion overall. Cool. All right, thanks a lot. That's all I had for